We're very pleased to have next speaker, plenary speaker, Juan Maldacena from Institute for Advanced Study in Princeton. Juan did undergraduate studies in Argentina and then came to Princeton for his PhD studies, and he defended PhD thesis under supervision of Kurt Cullen in 1996. That was a very special year. There were great students in Princeton. I remember that period very nicely. So Juan, after that, in the next few years, did some groundbreaking results in many different subjects. Actually, his papers from that period changed the entire discipline of theoretical physics as far as I would think about it, because the ADS-CFT correspondence is everywhere in string theory, in high-energy physics, in condensed matter physics. And but Juan did not stop on that. He continued influencing the subject, and his current passion, I understand, is related to black holes. So his talk today is about black hole entropy in Hawking radiation. Thank you, Juan.
Okay, thank you. So let me share the screen. Okay, I hope you can see the screen and you can hear me. Okay, so I will be talking about the entropy of Hawking radiation, and this talk will discuss recent progress on the black hole information problem, and is largely based on a review that we wrote with these authors here. And the current interest in this problem is due to two very important papers that appeared in 2019 and that led to many follow-up papers. There are also separate but very closely related papers by Salchenker and Stanford. And you can find a longer list of references in our review. So this talk will be about certain aspects of quantum gravity. And so quantum gravity is the quantum mechanics of the space-time geometry. And it will be using a formalism or an approach which is called semi-classical quantum gravity, which consists of starting from a classical solution, a classical geometry. And then we consider quantum fields propagating on this classical background, including gravitons, as the next approximation. And this leads to a well-defined approximation as an effective field theory. Of course, in each ordering perturbation theory, we have new coupling constants, so it's not absolutely well-defined, but it's well-defined as an effective field theory. And the effective coupling of the effective field theory is of order L Planck over some characteristic length scale squared. And this characteristic length square, in the case of, let's say, a Schwarzschild black hole, is of order the Schwarzschild radius of the black hole. And then there are, in principle, non-perturbative effects, which are naively very small, of order 1 over this effective coupling squared. Or in the case of the black hole, this works out to be a number of order e to the minus the entropy of the black hole. Now, we will consider situations where naively non-perturbative effects, which look like they're very small, in the regime of parameters that we will consider, actually will lead to large corrections to some observables. And these effects will be calculable within semiclassical gravity, and we'll have to include these contributions of non-perturbative saddles. Now, in other words, when we think about quantum gravity, we should be imagining that what we're trying to do is do a functional integral or a sum over different geometries. And so in the situations we'll be interested in, we'll have some certain boundary conditions we want to keep fixed. And then we sum over all ways of filling in the geometries with those boundary conditions. And so if we consider small deformations of a given geometry, then those are perturbative. Those will be included in the perturbative contributions. And in some cases, we'll have contributions from geometries which might have non-trivial topologies. And all these sums are going to be approximated as a saddle point. So a saddle point is just simply a solution of the classical or semi-classical equations, plus perhaps some small fluctuations. But in situations where we have more than one saddle point or more than one solution, we expect that both contribute. Of course, the detailed question of whether they all contribute depends on the contour of integration and so on, which we will not address. So we will simply assume that they all contribute, and we will see that including those contributions, we get an interesting answer. Now, the more specific computations we'll discuss involve black holes, and more precisely, quantum aspects of black holes. So the outline of this talk is that first I'll remind you of the formula for black hole entropy, which is the area of the horizon, a formula that was introduced in the 70s. And now, then we'll discuss a new formula for the fine-grained gravitational entropy, which says that the entropy is a certain area, but not the area of the horizon, but another minimal area. I will explain that. So this is a notion of entropy and an entropy formula in the context of gravity that was introduced about 15 years ago. And then we will use these formulas to compute the entropy of Hawking radiation coming out of black holes, and we'll obtain a result that is consistent with information conservation as opposed to information loss. And then I'll discuss a slightly separate problem, which is progress on long-time correlators, which is another aspect of the black hole information loss. Now, what is a black hole? So a black hole is a particular space-time geometry, and it is convenient to represent it in terms of diagrams. So we will be seeing this diagram. So let me explain just the basic features of these so-called Penrose diagrams. So we have a 4-dimensional geometry, and we'll assume the black hole is spherically symmetric to draw these diagrams. And so there are 2 dimensions, which are the directions of the 2-dimensional sphere, which we are not drawing here. And here we are going to draw the time direction, which is roughly vertical, and the radial direction, which is roughly horizontal. And we'll rescale this radial and time geometry to, we'll apply a rescaling, which is infinite in the far away direction, so that the region that is infinitely far away is brought to finite location and corresponds to this blue line here. So this is the region that is very far away in the geometry. The rescaling was chosen in such a way that light-like rays, so the rays that describe the propagation of light, move at 45 degrees. So for example, a light ray that starts at this point here will come out and go to infinity and move at 45 degrees. So that's a radially outgoing light ray coming from the center of the star to infinity. So this diagram, this particular diagram here, is describing the collapse of a star that collapses into a black hole. The green part is the interior of the star, and the outside part is the region of vacuum outside the star. And so the white region is a portion of the Schwarzschild solution. The geometry develops a singularity in the future, so that's marked here in red. A light ray that departs, for example, from this point at the center of the star will not make it out to infinity and will fall into a singularity. And there is a last light ray that does not fall into a singularity and that just stays at the fixed sort of radial location or at the fixed size. And that last light ray is called the horizon. So it's a set of light rays that comes out from the center and forms a 3-dimensional surface. So it's 1 light ray per point on the sphere. And if you cross the horizon, then you are in some region, this region called the interior. So this you cannot escape and you'll fall into a singularity. So that's the geometry of the classical black hole. Now, when we include quantum mechanics, we find a surprise. So this surprise found by Hawking, which is that black holes have a temperature which is inversely proportional to its size. That means that the black hole emits thermal radiation whose wavelength is of the order of the size of the black hole. And this leads to also the fact that black holes have an entropy. So you can associate to them an entropy by using the first law of thermodynamics. And this entropy works out to be the area of the horizon in Planck units. So it's the area divided by length, which is a combination of g Newton, c, and h bar. which is about 10 to the minus 33 centimeters in nature. And so this implies that the macroscopic black hole has a huge entropy. Now, there is a property of Einstein's equations, which is that, well, it's a combination of Einstein's equations and a positive energy condition, a positive energy property of classical matter, which implies that the area of the horizon always increases. So if you have matter falling into the black hole, forming a black hole, then the area of the horizon here starts being 0 at the center of the star, and then it grows and it reaches a maximum here at the surface at this point, and then it stays maximal as the area well, of the Schwarzschild solution. And so this classical property of general relativity can be interpreted as enforcing the second law of thermodynamics. So one question we might have is that when a black hole emits Hawking radiation, it loses energy, and so its area becomes smaller. So what happens to the entropy? And now we should remember that the entropy of a black hole is not just this term, the area term, but it should include the entropy of matter that is outside the black hole. In fact, this was the actual formula that Bekenstein introduced in the 70s. But this matter term should also include the entropy of quantum fields. For example, the entropy of Hawking radiation. And if you include that, then this whole combination actually increases in the process of Hawking radiation. So the area term decreases, but the matter entropy increases more, so that the second law is still obeyed. And this was argued with some generality in relatively recently. So the point is that the full black hole formula, it's important to, entropy formula, it's important to include the entropy of the fields outside the horizon. And this entropy is UV divergent at the horizon due to the short distance entanglement we have in quantum field theory. We are defining the state of the quantum fields as in two portions, the region outside the horizon and the region inside the horizon. And that introduces a divergence, which can be absorbed into renormalization of the Newton constant in a procedure that is well understood. So I won't discuss that anymore, but that is throughout the formulas I'll discuss later today. So that's a small technical detail. But physically, it's clear we should include the entropy of quantum fields, because that entropy that entropy includes the entropy of Hawking radiation and forces the second law. So some of these results imply that a black hole is a thermodynamic object, which is surprising since it was just simply a solution of the classical Einstein equations. And these results have inspired certain central hypothesis. And this central hypothesis, we can call it a central dogma, dogma in the sense of assumption, and similar to the central dogma of biology, which tells us how information flows from DNA to proteins and so on. Here, it's also an assumption about information, especially quantum information. So it's an assumption about how black holes process quantum information. So this idea is that the black hole, as seen from the outside, can be described as a quantum system with s degrees of freedom, where s is the black hole entropy formula, so the area over 4G Newton plus whatever matter fields corrections, and that it evolves according to unitary evolution, at least as seen from the outside. So what this is saying is that the black hole can be replaced by a system of qubits, and that any observation that we do about the black hole as seen from the outside should reproduce, should be able to be reproduced by some interacting system of qubits. The assumption doesn't tell us exactly what the system of qubits is. It only bounds its number of degrees of freedom, and it asserts that there is such a system. So that's the assumption. Now in practice, we can introduce some imaginary cutoff surface that separates the black hole and its near horizon geometry from the rest of the system, from the rest of the space-time. And so the idea is that we can replace everything that is within this cutoff surface by, again, the system of qubits that we were discussing. Now, this is this is an assumption. It's not something that can be derived directly from Einstein's equations, and it's an assumption that is somehow behind some of the language that we use to describe the system. But we will not be assuming this in our talk. So I'm just talking about this specific assumption just as a background knowledge, but we will not be assuming this assumption during this talk. Now, there is some evidence for this assumption that comes from string theory. And there are two pieces of evidence mainly. One is the counting of the entropy of black holes. So in certain very special black holes, in special supersymmetric theories, they can be counted very precisely using strings and d-branes. And that reproduces the area formula that we discussed before. And not only that, but also calculable corrections to this formula. Then there is the ADS-CFT correspondence, which says that if we have a black hole in anti-de Sitter space, it can be understood as a hot fluid of strongly interacting particles on the boundary. So if you assume this duality, then also that central dogma would be correct. But as we said, we are not assuming this assumption. We're not going to even assume string theory during this talk. I'm just mentioning this just as background knowledge. In fact, there are people of the opinion that assumption actually can't possibly be true. So let me now present their arguments. And Hawking presented this argument in 1976. So this argument is based on considering the geometry of an evaporating black hole that's been made from collapse. So the geometry looks similar to the one we had before. Now we have the Hawking radiation that consists of entangled pairs of particles. So one goes to infinity and the other goes into the black hole horizon. So these are just entangled pairs of particles that are already present in the vacuum, but in the context of black holes, because of the presence of the horizon, they suffer, each of the members of the pair suffers a different fate. One goes to infinity, one goes to the singularity. And so we have the radiation that comes steadily out of the black hole, and that causes the black hole to lose energy, and the area of the horizon to shrink, and the mass of the black hole to shrink. And then at some point, we expect that the black hole evaporates completely. We don't know exactly what happens at the final points of black hole evaporation, but we'll assume that that after the black hole evaporates completely, we end up with flat space. And this portion here is just the part of the Penrose diagram of flat space. So here, this vertical line is r equal to 0, so the origin of coordinates in flat space. So what we see is that if we restrict to observations done here in the future, we end up with a mixed state. We end up with a mixed state because these partners of Hawking radiations are entangled with the partners here in the black hole interior. And okay, in other words, we have a picture which we can roughly draw in this way. So we have some process. So we start from flat space, and we have some process that appears to create a second universe, which is the whole black hole interior, which at the end becomes disconnected from the outside universe. And in these two universes, we have one member of the pair of the Hawking pair. In the other universe, we have the other member. And so we have a situation where we created a pair of entangled particles, and we're observing only one of the members of the pair, and therefore we have some non-trivial entropy. Of course, if we observe both members, then we would have a pure state. However, the causal structure of spacetime suggests that we can only access these members. So that's the argument. So it's a perfectly reasonable argument, and we would like to understand whether this type, well, whether there's something wrong with this argument or exactly how this is resolved. So now we'll have a more detailed look at this problem, and the more detailed look involves computing not just the entropy of the final stages, but the entropy as the radiation is coming out of the black hole. So as the radiation is coming out of the black hole as a function of time, the radiation increases monotonically. It doesn't have to be a straight line. That depends, the particular shape depends on the special properties of the black hole and the matter around the black hole and the quantum fields that we have. But what is true is that it rises monotonically. On the other hand, the area of the black hole that defines the thermodynamic entropy of the black hole and the number of degrees of freedom decreases steadily. Now the contradiction, so Don Page noticed that there is a contradiction with that central dogma at the time when these two lines cross. That's called the Page time. So at this time, we have some entropy in the Hawking radiation, but that entropy could arise from entanglement with some of the degrees of freedom in the black hole. However, at this point here, because the entropy is bigger than the total number of degrees of freedom in the black hole, this entropy cannot arise from entanglement with those degrees of freedom. So at this point, we have a contradiction, an apparent contradiction with that idea, with that central dogma. So if this process of black hole evaporation is unitary, then it should follow this purple curve, which is the so-called Page curve. So that's what we expect for a unitary black hole. So now for resolving this paradox, it is crucial to use a formula for the gravitational fine-grained entropy. And we will later discuss its derivation. So before we discuss the formula, I should remind you that in this talk, we are using two notions of entropy. So one is the main star of this talk is the fine-grained entropy or Foyn-Neumann entropy, sometimes also called quantum entropy, which is defined as trace of rho log rho, where rho is the density matrix that describes the quantum system. So the quantum system could be pure or mixed, and it's characterized by density matrix rho, and we can calculate the entanglement, the von-Neumann entropy. Sometimes in thermodynamics, we also define a coarse grain or a Boltzmann entropy that obeys a second law that can increase under unitary evolution. So we will not define this entropy precisely. I assume you might encounter it in your thermodynamics courses, but we will concentrate on this entropy. Here I'm only mentioning this because it's important not to confuse these two notions of entropy. And we'll see the difference between these two entropies in an example. So imagine that we have a big box with a little box inside containing some gas. The initial gas has some entropy. And then we open the box. This is a unitary process. Then the gas comes out and fills the bigger box. Okay. So the quantum entropy, or fine-grained entropy, or von-Neumann entropy is given by this for the initial state. And since this is a unitary process, there's a final density matrix, which is given by this expression conjugated by the unitary evolution. And we get the final entropy, which is actually equal to the initial entropy. Okay, that's the statement that it's preserved under unitary evolution. On the other hand, this is a type of process which, as you know from your thermodynamic courses, the entropy, the usual thermodynamic entropy increases. Okay, so the coarse grain entropy or Boltzmann entropy actually increases. So for the moment, we'll be talking about the entropy of the black hole as seen from the outside. And this is the entropy of the quantum system that appeared in our central hypothesis. Now, the first observation is that the horizon area computes the thermodynamic or Boltzmann entropy because it obeys the second law of thermodynamics. In fact, we saw that it increases when the black hole just forms. So the question is, can we compute the fine-grained entropy? Now, it's interesting that it's very interesting that there is actually a formula for the fine-grained gravitational entropy, a proposal, where the entropy is given by a formula that starts out similar to the generalized entropy formula. So this formula says the following. So imagine that we want to compute the entropy at some time t. So this purple line is roughly this cutoff surface. So we have an imaginary surface that surrounds the black hole, a few Schwarzschild radii outside the black hole, let's say. And we consider some spatial slice that ends on a particular surface. So surface in this diagram is just a point because we are not drawing the directions of the sphere. And then we calculate the area of the surface and the entropy of the quantum fields on this slice. So we get this expression. And then we move the position x of the surface. So we move it in or up and down until this develops an extremum. Okay. Extremum means that the first derivative in the vertical direction or horizontal direction both vanish. Okay. And that surface is sometimes called a quantum extremal surface. It just means that we did this extremization process. And then if there are multiple surfaces, we just take the minimal one. So a crucial point is that we're allowed to take the surface to the interior of the black hole. And in particular, this implies that the final answer that we get depends on the geometry of the interior of the black hole. So this formula can also be derived from the gravitational path integral. And I'll very briefly sketch the derivation later. So historically, it was first presented as a proposal, and then it was understood how to derive it from the semiclassical gravitational path integral. So let me show you some examples. So let's consider this black hole just after it collapses. So this is the same geometry that we were discussing before. The black hole just after it collapses. It turns out that the surface that extremizes that formula is one that has zero area. So we can take the area all the way to zero by shrinking it here at the origin of the coordinates. And then if we compute the entropy there, we'll have the entropy on this slice, and this will include and will be essentially equal to the entropy of this star. So this is here we're considering the entropy just after the black hole forms before it emitted a significant amount of Hawking radiation. And if the star was in a pure quantum state, this is not the real star, but some imaginary star, then the entropy would be zero. Now notice that we get the same entropy as the entropy it had just before it collapsed. And that's different than the area of the horizon or the thermodynamic entropy, which increases rapidly after the black hole collapses. So here we see that these two notions of entropy and two different formulas for the entropy in gravity, and one gives us a result that is consistent with the von Neumann entropy, and the other, so the area of the horizon, gives us the result consistent with the Boltzmann or thermodynamic entropy. So there is, we could consider the full Schwarzschild solution, which contains two black holes, one on the left, one on the right. And if we consider the entropy of the right black hole, then the minimal surface is at the bifurcation surface with the two future and past horizon meet. And in this case, the area is actually equal to the area of the horizon. And so the von Neumann entropy in this case is actually equal to the thermodynamic entropy. We can now consider an old evaporating black hole. So in particular, the evaporating black hole at late times. So we have, again, the same figure of the evaporating black hole, and we consider some late time t. And if we consider a spatial surface at this late time, then it was realized, and the important result was this paper by 2019, that there is a certain extremal surface that is very near the black hole horizon. And so let me just explain why there is such a surface. So if we imagine moving this surface along this slice, so it's at late time, so there will be some area of the horizon at this point in this region. But as you move the surface inwards, you will find that the entropy increases again, and it increases because we are including the entropy of all these partners of Hawking radiation that have long left the system. So for example, this green one and the red one here that have left the system. And all those will start contributing to the entropy. And by late times, I mean times after the page time, and this entropy grows to be very big, much bigger than bigger than the area of the horizon at this point. So roughly this curve has a shape like this. And the important part is there is some minimum, and there is some quantum extremal surface here near the horizon, which has an area of the order of the area of it has a total entropy which is of the order of the area of the horizon. And so, but this was about the entropy of the black hole. And so we get what we expected, that the entropy of the black hole, well, is never bigger than the thermodynamic entropy, and that's good. But that doesn't yet solve our problem, because we would like to understand the entropy of the radiation. And when we compute the entropy of the radiation, so the radiation appears to be in a mixed state. The radiation is far from the black hole, so we might think that we do not need to understand any details of gravity to calculate this entropy. But the radiation appeared to be in a mixed state because we have used the formulas that come from the evolution of gravity, and so we should use the gravity rules to compute the fine-grained entropy. So the bottom line is that even though the radiation is far away from the black hole, where the effects of quantum gravity are supposed to be small, due to the fact that we computed that state using gravitational evolution, we should use the gravity rules to compute the fine-grained entropy. And the gravity rules allow us to instruct us to consider this, to consider this generalized entropy formula that allows us to introduce certain surfaces in the space-time and compute the entropy. And now, which is the region that we have when we compute the radiation entropy? So naively, it's this region that is outside the black hole, and we should compute the entropy of the quantum fields here. But the gravitational entropy formula allows us also to say, okay, we include also this part of the spatial slice, and we include the area of this surface, and also the entropy of the quantum fields here. So naively, we might think, okay, we are adding something positive because we have the area of this the area of this surface, and we are adding something here. But the reason that this might be convenient to do, and that it is the right thing we should do, is that when there is entanglement, or there are quantum fields that are entangled between the interior and the exterior, we can decrease the entropy of the quantum fields by including this region. So in this particular case, we are having the Hawking radiation here on the outside and the partners of the Hawking radiation in the inside, and that decreases the total entropy of the quantum fields. So then we use this formula, and using this formula, we get a result for the entropy that is also proportional to the area of the horizon of the black hole at late times. And now this is, this as the same as the previous formulas. It's a funny formula, which is telling us what the entropy of the exact state is if we were to include all the corrections of quantum gravity. And it's giving us that formula in terms of a computation that uses only the semiclassical state. So the original saddle point solution, or the original, the solution that describes the main evolution of the black hole. So by doing a computation in this approximate solution, we get an approximation to the entropy of the exact state. So in this way, we can compute the entropy of radiation, and it leads to this page curve as we were expecting. Okay, so in this way, one derives the entropy of Hawking radiation from the rules of gravity. Now you can say that this is just an accounting trick because we are using the same geometry and just redefining what the entropy is. But this is the accounting rule that gravity instructs us to use. And this type of accounting rule, so this gravitational entropy formula, was actually derived before it was applied to this specific problem. So it wasn't just designed and invented for solving this problem. It was developed in order to understand better some aspects of ADS-CFT, but they were later applied to this problem, and so on. So now we have used this gravitational fine-grained entropy formula, and the question is whether this is the right formula for the entropy. Okay. Now we will not directly talk about the derivation of the formula. Instead, we will concentrate on a slightly simpler problem, which is conceptually similar. And if you understand what we are going to say right now, the derivation of the entropy formula is not too much more complicated. So we will calculate the trace of rho squared, where rho is the matrix, the density matrix of the system. This quantity is sometimes called the purity, and for a pure state, the trace of rho squared is equal to 1. So there's a single state here, and that gives us just 1. And for a highly mixed state, it gives a result which is much less than 1. So this is something that can distinguish between pure and mixed states. That's why it's called the purity. But in our work, in what follows, we will work with unnormalized density matrices. So we will be really comparing trace of rho squared versus trace of rho all squared, which is what and the ratio of these two things is the trace of the normalized density matrix. So we'll now consider again the fully evaporated black hole, and we'll use it to compute the density matrix of radiation. So we'll have the, so this type of evolution will say conceptually looks like this. So there is some matter that follows the black hole, and there are these entangled pairs. And we'll just compute the entropy of, we'll compute the density matrix of radiation, and we'll compute not the entropy, sorry, I misspoke. We'll compute the purity of radiation. So trace of rho squared, for rho being the density matrix of radiation. So the density matrix can be computed by thinking about some evolution for the bra and some evolution for the ket. And this gives us, then we can take the matrix elements, ij of the density matrix, will involve projecting that state into some state, let's call it I, of the Hawking radiation for the bra, and the other similar one for the ket, okay? And then this radiation is entangled in some way with the interior, and we'll have to say what we do with the interior, and we'll say it as we compute it. So for example, if we compute the trace of rho, then that will be given by summing over these indices. So we identify the index I and j. So we sum over these indices, and it turns out that to compute this, it's convenient to connect the two interiors, we get a result which is conceptually what we would naively expect. So we trace out over the interior. So that's what it means to connect the interiors. And we get the result where we are summing over these indices. So here the purple line is representing the Hawking radiation entangled with its interior partners. Sorry, I should have said that. And so we are tracing over this, and we have a single loop of indices. So we get the result which is proportional to the entropy of Hawking radiation as computed by Hawking. So let me denote that as the entropy of Hawking radiation as computed by Hawking. And this result is of order the black hole entropy. So it's some factor times the black hole entropy. Now we will compute trace of rho squared. And when we do that, there are two possible saddles. So let me first start describing the Hawking saddle. So the one that Hawking would have computed to compute this trace of rho squared. So we have now two copies of the system because we have two factors of the density matrix. So we have the copy 1, which was the same as what we discussed before. And then we have the copy 2, which is very similar, except that the index I and j are exchanged. And when we sum over the indices, we should be identifying, that results in an identification of this future part of the geometry here with the future part of the geometry here. So this looks more like a bra evolution to the future, and this looks more like a ket evolution towards the future, and this looks more like a bra evolution towards the past. Okay. If you know what I'm talking about, this is a bit like a Schwinger. It's a portion of a Schwinger-Keldysh contour. If you don't worry about it. Now, then we connect, so the two saddles that we'll be discussing differ in how we connect the two interiors, the various interior regions that we have here. So in the Hawking saddle, these two interiors are connected among the two interiors that appear in the computation of a single density matrix. So this density matrix looks like we are tracing out over the interior, and we get some mixed state here, and we take now the square of that. And because of the way that the indices are identified, we have just a single loop of indices here. So we start, let's say, from index I, we go around here, we go to the index J, which now is identified with I, and we go to the second copy, and again, we go around again. So there is only one overall sum over the indices, and so trace of rho square will be of order e to the sh, where again, sh is the total number of states of the Hawking radiation, and that's the entropy of the Hawking radiation. And so when we compute the normalized purity, so the trace of rho squared over trace of rho all squared, we get the result, which is e to the minus sh. Remember that, so this was e to the sh, and the denominator before we take the square was also e to the sh, therefore we get e to the minus 2sh because this is squared. And so that's consistent with a state that is highly mixed. In other words, it has a large entropy. Okay, now then there is a second saddle, which sometimes called the wormhole saddle, which consists in, so we have the same pattern of index contractions outside in the entropy of the Hawking radiation in the space-time, but we are allowed to connect the interiors in now a different way. So the interiors live in this region that is subject to quantum gravity, where quantum gravity effects might be important. And so we can consider this different way of connecting the interior. And with this new way of connecting the interior, it turns out that that we have really two index loops. So perhaps let's look at, for example, the blue index. So here, the blue index, well, starts here, and then it goes out to the other side, and then goes back through the black hole interior and comes back to this original side. So if we now draw this solution differently by taking this, let's say, ket piece of this solution and the bra piece of the second copy, and the indices are connected just between these two pieces. And then for the second bra and second ket, we also have a second connection of indices. And so we have now two separate index sums, and we have trace of rho square is e to the 2 sh. So we have a bigger result, and then the ratio, this ratio is now of order 1, which is consistent with a pure state. And now the crucial point here is that in quantum gravity, we expect that we should add overall geometries, and this so-called wormhole contribution is actually larger in this regime, and it dominates the calculation and gives us a result which is consistent with unitarity. There is still, it's not perfect. So this discussion is not perfect because we've also have the other Hawking saddle, which gives us a small correction to this one. And this is something that needs to be understood. So there is some partial understanding of that. But at least to first approximation, we get a result that is consistent with unitarity. So we see that the purity or trace of rho squared is what we expected for a pure state. And we see this directly from a gravity computation by including all the relevant saddle point geometries. Now, if we want to compute the entropy computation involves a similar manipulation that involves n copies as opposed to 2 copies of the system. And then we need to do an analytic continuation in n. This is sometimes called the replica trick. And from the wormhole contributions, we go to this gravitational fine-grained entropy formula that we discussed, even this formula which had these additional regions called islands in the interior of black holes. So the conclusions, at least up to now, is that we reviewed the thermodynamic black hole entropy, and we described the fine-grained gravitational entropy formula, and we applied it to the computation of the entropy of radiation, and we got a result which is consistent with unitarity, with information conservation. A lot of what we discussed was derived by thinking about aspects of ADS-CFT, which itself was derived using string theory. But we didn't use any string theory in this talk. We only needed to use gravity as an effective field theory to apply these formulas. So gravity actually contains a lot of information, and this information involves the black hole interior, and if we use it properly, then you get nice results. Now, in the last few minutes, I'll briefly discuss some other aspect of the black hole information problem, on which also there was some recent progress. And this topic deserves a full talk, but I'll just mention a few words. So there is a form of the information paradox that involves corrections to the long-time behavior of correlators. So if you perturb a black hole, so naively the perturbation falls behind the black hole horizon, and the effects of the perturbation are lost. So in the far future, the black hole returns to some thermal equilibrium state if we had some black hole in thermal equilibrium. However, this cannot happen in a system with a finite number of degrees of freedom. So if you make a perturbation to a thermal density matrix, that perturbation cannot disappear completely. So a system should remember. And these corrections are due to the discreteness of the energy eigenvalues and the finiteness of the entropy of the black hole. And these correlators, these long-time correlators, have a feature which is roughly characterized in this talk. So they typically decay. So that's just the thermalization. That's just the fact that the black hole absorbs the perturbation. And then at very long times, it reaches some kind of plateau where that correlator sort of oscillates and has some intricate pattern of oscillations or quantum noise that depends on the precise energy eigenvalues of the system. And in between, it has a period of where the correlators decrease and then they increase again. And that this ramp has to do with is related to the repulsion of eigenvalues and some spectral properties of the eigenvalues. So notice that the vertical direction here is exponential, and this plot was made for a simple toy model with a finite number of degrees of freedom. It's called the SYK model, so it's a model for interacting qubits. So this is what we expect for a general unitary system for these long-time correlators. In this particular case, the long-time correlator involves computing the partition function of the system, so the trace of e to the minus beta h, but where we have beta plus I t, so it's partly Euclidean, partly Lorentzian evolution. Okay, so the recent progress was the realization that you can get this ramp region by a certain wormhole geometry, which is given by taking the Schwarzschild solution and making an identification of Schwarzschild time. So this identification of Schwarzschild time is with period t, and is related to the fact that we are taking this trace here. And then this wormhole geometry gives us the average over these correlators. So it doesn't give us the fluctuations or the quantum noise. It just gives us an average. And we can get this average by averaging over time or averaging over some microscopic couplings of the theory. And so that's and not only one gets that, but also some other properties of the quantum noise can be obtained by some more complicated wormholes. So these saddle points in the gravitational path integral gives us some average results. And if the theory is uniquely defined, we expect that some other contributions generate the noise, which is of the same order as the average signal. And this is understood in some toy models, but not yet understood in the full gravity theory. And it's expected that to understand this, it will require a full definition of quantum gravity, perhaps using string theory. Now, the idea that random couplings give rise to geometric connections and wormholes was suggested in the past. There were developments in the 80s by Coleman, Giddens, and Strominger. And now we're seeing that these effects convey useful information about the statistics of energy levels or matrix elements of operators. So in conclusions, we are seeing rapid progress in understanding how space-time geometry and quantum information are related. So I mainly discuss in this talk this entropy of Hawking radiation, but also there is progress in understanding the statistics of matrix elements and long-time correlators. So there are many future open questions. So we would like to understand better what this is teaching us about the interior and about the singularity of the black hole in particular. So these effects can be computed even though we don't yet understand how the singularity is resolved. And also we would like to extract some lessons for cosmology that hopefully at some point in the future we'll be able to relate to experiments. Okay, thank you.
Thank you. So let's see if we have questions in the audience or online. Anton?
Hi, Juan. Thank you for a nice talk. I have a kind of naive question. So you've explained that there are two saddles, right? One of them is a Hawking saddle, and the other one is this wormhole saddle. And actually, the wormhole saddle dominates. But does it mean that we as a humanity should not be seeing subleading Hawking saddle, and then as a consequence should not be expecting to see Hawking radiation, right? Because that picture corresponds to some kind of subdominant solution. Maybe it's just could you comment on that?
Yes. That's a good question. I perhaps should have, let me explain this better. So let me go back to the relevant, right. So it's important here that what we are doing is computing a particular observable, which is the trace of rho squared. And so the Hawking saddle is subdominant in the computation of trace of rho squared, okay? In fact, it gives us a small answer compared to the other saddle. But that's because we are considering a specific observable. So let me try to explain this in another way. So we are considering, if we are looking at some unlikely event, right? It might be that the Hawking saddle is not the best one to calculate the probability of that unlikely event. We have to be careful that that there might be some other saddle somewhere else that gives us something more likely, okay? And this is something that is very important when we are computing probabilities, that if we are using one saddle, is like using a certain Gaussian approximation for some observable. And if we are getting a very tiny answer for that observable, we should really look at whether there are other saddles that give us a bigger answer. This is true in many fields. Let's say in economics is famously what maybe can cause crashes, market crashes, and so on. But in this case, we see just from the calculation itself that when we calculate this quantity for the Hawking saddle, we get a very tiny answer, okay? And then if we compute it for the wormhole saddle, we get a bigger answer, okay? So that's because we are computing a very special observable, trace of rho squared, which gives a tiny answer for the case of Hawking radiation. So I'm not sure if I hopefully I answer your question.
Yeah, thank you.
Sorry, maybe I should say it differently. If we were computing a different thing, like for example, simply the expectation value of a simple operator, like what the photon field is doing outside the black hole. So that's a simple operator. And for that operator, the expectation value of that operator will be correctly given by the standard Hawking solution, just the standard spacetime. So if we are looking at the simple property of the black hole, it will be computed by the usual, the standard solution. Mm-hmm. But the quantities we're discussing here are very sensitive to the, to the finite, so they are very detailed observables.
Thank you.
Sure. Other questions in the audience or online? If not, then I have a question, Juan. So if I think about the JT gravity case and Saad Schenker and Stanford paper, then this the dogma side of the story would be the SYK model, right?
Yes.
So in that case, we know what is that qubit quantum system is. Any
Yes,
clue
yes.
whether there is some universality or it is specific that SYK would give us the right thing? And now let's take to 3 + 1 dimension. Any hint what can be this dogma
Right.
qubit system?
So I think what Samson is talking about is this fact that some theories of gravity seem to involve actually not a quantum system as defined in this central dogma, but an average of quantum systems.
Yes.
And we don't understand whether this is something that is general to general theories of gravity or special to special theories such as very simple models of 2D quantum gravity. So there is one particular theory of 2D quantum gravity for which the central dogma is actually not true. What is true is that theory of 2D quantum gravity is dual to an average over quantum systems. So we have a Hamiltonian, as suggested by that central hypothesis, but the Hamiltonian is drawn from a random ensemble of Hamiltonians, and gravity is telling us some properties about this ensemble. Gravity determines the ensemble and is dual to the full ensemble, not just to one particular quantum system. So we don't know whether that.
Yes. Did we lose a connection?
Yeah, looks like we lost the connection.
Well, maybe we wait a minute. Can we restore? Oh, Juan, we lost you for a minute.
Okay, good. So maybe I'll just repeat the.
Before you repeat, actually, I want to say in this one that is it possible that this average over the theories actually is another quantum theory that just looks like averaging? Because, I mean,
that's also possible that we need to consider a bigger quantum theory.
Right, so maybe we did not identify correctly in the case of JT gravity.
The thing is that we want to say that the entropy, for example, is finite, and we have a finite dimensional Hilbert space. That's true for each element, but if you include the couplings as an additional part of the Hilbert space, then that might be infinite dimensional because they are just classical variables.
Okay. So let's thank Juan for inspiring talk as usually. Thank you so much. And
Well, thank you very much.
bye-bye. So now.